semester are given to creating a lot of sparks, and they generate a lot of electrical noise. And so, as a consequence of that, I was building your lab assignment number 4 over this weekend, and this is a variation on something that I've assigned in a different class for about 10 years. And so I hooked it all up, and as soon as I got the motor going, it caused my 328P to reset. That's strange. Hooked it up again, and it caused the thing to reset. I hooked it up again, and then it caused my USB port to reset. That is the USB port on my laptop stopped working temporarily. So I brought out an oscilloscope, and the oscilloscope that I used was one of these ADLM2000 modules that you all, I believe you all have one in your possession. You got these when you took ECE 210, Circuits and Electronics, and I'm told that you still have them. Anyway, I hooked that up to see what was going on. That device kept getting reset. And so what was going on is that my motor was making a heck of a lot of electrical noise. So much so that it was very difficult for me to just build a simple experiment of motor control. And so, and I had gotten inquiries from a few students about some difficulties. So I decided, since I don't really have a good handle of what's going on, what my current thinking is that the motors that we sourced for the class this year generate a very substantial amount of electrical noise. And you don't have the parts in your kits that you would need to deal with all of that electrical noise. So rather than have you go through on your own without access to all the laboratory supplies I have, I decided I'm going to delete the whole motor part of lab assignment number 4. So you probably got 2 emails from me yesterday, one that I posted on Piazza and then one I posted on Moodle, where I was letting you know I'm changing lab assignment number 4, just dropping out the motor. Forget the motor. Don't hook up the motor at all. Don't use it. And so this amounts to a considerable simplification in the circuitry for lab assignment number 4. But the idea is, instead of having a variable speed motor, you push the buttons and the motor is different speeds, just have a variable brightness LED. And the principle I'm trying to teach you here is pulse width modulation, which is one of the modes of the timers that we've been talking about. And so it's precisely the same code, whether you use it to control a motor or you use it to control the brightness of an LED. And I'll walk you through all that today. But I'm making this change because the motors, they just generate a lot of electrical noise. I'll give you an example of what it is using a test rig that I hooked up. So now some of you may have already solved this problem. You may already be well underway. You may already have a motor controller working, and that's fine. And so if you want to ask, can you use the original unmodified assignment? Instead of this modified one, if you wish to, yes, you can. I don't advise it, but you can. So there are sort of 2 flavors of lab assignment number 4. There's the original one, and then this new one is just get an LED, any color. You can use a red LED, green LED, and we just want you to change the intensity, the brightness, the intensity of it, and I'll show you how to do that. Let me just pull up the chat. Let's see. Yeah, the question is what should you use with motors to take care of some of the noise? I'll get to that at the end of the class. Okay, so that's the situation with lab assignment number 4, which is due a week from Thursday. Okay, we're talking about using the timer counter. It's really called a timer counter, but we're just going to call it a timer. And so to just get us all kind of on the same wavelength in terms of terminology, I just wanted to put up some definitions here. And what we have done so far using the timers is we created a square wave. And so when we say a square wave, what we mean is a pulse train, a train of pulses, right? where the pulse is high, and then it's low, and then it's high, and then it's low, and it's high for 50% of the time, and it's low for 50% of the time. Okay, and now the thing that matters there is the period of that. What is the time that it takes for this thing to repeat? And so we call that the period, capital T. You've seen this certainly in other classes, but just to make sure we get it, that's the period T. And we also care about the frequency of that waveform. That's 1 over T. Okay. So just the thing that's going to be new today is that we're going to vary the duty cycle. That is, given that the period is T, it repeats every T seconds. What we're interested now is varying the amount of time that the waveform is on as opposed to when it's off. And if we call that lowercase t, then what we're doing is we're changing the duty cycle. And the duty cycle is going to be a number between 0% and 100%, and it's just t, little t divided by big T. So that if the waveform is always off, we'd have a duty cycle of 0%. If it's on half the time, off half of the time, that's a duty cycle of 50%. And if it's always on, that's just a 100% duty cycle. Now, when we talk about the waveforms that we're creating with our Atmega 328P, we're powering up that chip with 5 volts. So those output pins are going to be 5 volts or 0. I mean, they may deviate by a small amount from 5 volts and 0, but we neglect that deviation. And so the amplitude when it's on is 5 volts and when it's off is 0 volts. Okay. And so what I showed you on Wednesday of last week is that we configured a timer and had it generate a square wave of certain frequency, and we played that into a piezoelectric speaker, and we could hear the tone there. I mean, I had to. I was getting some. Zoom was filtering out some of those tones, but I believe I have that fixed now. So we were just playing a square wave. When it's on, it's 5 volts, and when it's off, it's 0, and that was causing that piezoelectric speaker to deflect or deform the way we discussed last week. So I'm going to do a little bit more of that today, but then after that, I want to get into how we vary the duty cycle of that. And if you wanted to change the brightness, the intensity of an LED, or if you wanted to change the speed of a motor using something like the 328P, the thing about a motor, a DC motor, is its speed is going to be proportional to applied voltage. So you give it a low voltage, a certain voltage, it's going to spin at a certain speed. Crank up the voltage to a higher level, and it's going to spin faster. And so that really requires an analog voltage. And the 328P doesn't actually have an output that's analog. You can't vary the output between 0 and 1 and 2 and 3 and 4 or 5 volts. The output is either 5 volts or 0, right? Our GPIO pins are high or low. But it turns out when you do this, what we call pulse width modulation, that is, you send out a train of pulses at a fairly high frequency, hundreds of hertz, and you change the duty cycle, then that actually has a variable DC component in it that can be used to change the speed of the motor. And so what happens is the motor is only responding to the average value of the signal. And so I'll show you how that can change the speed of a motor. I'll do the demo here. I don't want you to do it because there's just too many electrical noise issues for you. But you can also use that to cause an LED to dim or to appear to dim. And what you're doing is you're fooling your eye because of retinal persistence into believing that the LED is dim or bright based on this. This is pulse width modulation. So that's the new trick for today. And so just to review what we talked about on last week with regard to the timers. So on your Atmega 328P, there are 3 timers counters, right? They're called, sometimes you call them timers, sometimes you call them counters, sometimes you call them timer counters. We're just going to refer to them as timers. And they're numbered timer 0, timer 1, and timer 2. And timer 0 is an 8-bit counter, meaning that the heart of this counter is an 8-bit register. You can think about it as having 8 flip-flops in there, and then it's configured to just count up. It'll count from 0 to 255, back to 0 to 255, and it'll keep doing that, right? Or we talked about how we can preload it with a certain value. So instead of starting at 0, it starts somewhere else, and it counts up to 255, and it overflows. Timer 1 is 16 bits, so it counts up from 0 to 2 to the 16 minus 1. So that's 65. Whoop, this should be a 5. It counts to 65,535. So it can count over a much wider range. And then timer 2 is also 8 bits. And these timers have many, many features and modes associated with them. And so there were 2 registers that matter. If we talk about timer 0 in particular, right, timer 0, then the 2 registers are TCCR0A, that's the timer counter control register 0, register A, and then TCCR0B. If we were referring to timer 1, then you'd put a 1 in there instead of a 0. And if it were timer 2, you'd put a 2 in there. Okay, and so they have all these bits on them, and we just talked very briefly about some of those bits. So it turns out that these 3 bits, which can be set as high or low, right? And there are 3 bits that can all be set high or low. So that means that there are 8 possible combinations there. And those bits WGMO2, WGMO1, WGMO0, and I can't even remember what that acronym stands for right now. It has to do with the mode. In any case, you may notice that in your textbook, and if you look at the data sheet, they refer to this as WGMO2:00. That means number 02, 01, and 00. This is a shorthand for that. Okay, so this is a shorthand for writing the bits between the bits 2, 1, and 0. Anyway, they configure the timer mode. And so we use the normal mode so far. I'm going to show you that again, and then we're going to use fast pulse width modulation. We also looked just so briefly at these 3 bits, and those bits select the clock divider. And the deal here is that you have a master clock oscillator driving your 328P, and that's telling it how fast to do things, how fast to go and grab an instruction from memory and execute it, grab an instruction and execute it. And we're using a 16 megahertz clock. So everything is happening at 16 megahertz, which is slow in computer time, but it's pretty fast in people time. So what we often will want to do to get bigger delays and lower frequency waveforms is pre-divide that by one of these dividers. And so those bits CS, 02, 01, and 00 are used to select different pre-dividers. So that instead of driving the clock always with 16 megahertz, you can drive it with 16 or with 2 megahertz or with 1/4 of a megahertz or even less. So that slows down the counter so that you can get delays that will produce waveforms that we can see, hear, and respond to, on sort of people time. Okay, so just to review the normal mode, right, with timer 0, this is what we did last time, and I'm going to do it again in a different way. The first thing we had to do is configure the timer. That is, we had to put some values in those registers that told it, run in normal mode, and here's the delay, here's I want you to divide the clock by a certain value. So we have to configure it. Then we got into a loop, and in that loop, we preloaded the timer counter register. If we didn't do that, it would start at 0. But if we wanted to make a delay of a certain amount, we figure out what's the delay associated with each tick-tock of that thing, and then we count up how many such tick-tocks we need to give us the delay. We preload the counter with a delay. Then it starts counting. It's just counting up. We wait till it overflows, and once it overflows, we clear the overflow flag, and then we loop again. So that's how we've been doing it. And I want to show you an interesting example that I hope we're able to see and hear well over Zoom. And here's the demo. Is I'm going to have a square wave of increasing frequency, and I'm applying that to an LED, a blinking LED, and to a piezo speaker, and also to an oscilloscope using this ADALM 2000 scope that you have. So I'm going to vary the frequency from a really low frequency where you'll just see the LED blinking on, off, on, off, on, off, on, off. And you'll hear the piezoelectric going click, 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 click. and you'll see a waveform on the scope, and the scope will tell us what the frequency is. And then we're going to crank up the frequency higher and higher and higher. The LED is blinking faster. The piezoelectric is going click, click, click faster. We're seeing it on the scope. And eventually, it's fast enough that your eyes can no longer see the LED blinking. It looks like it's on all the time. And your ears can no longer hear click, click, click. Instead, they're just hearing a tone, because that's the way our ears are built. And so here, let's walk through some of the guts in this. Okay, so I'm using timer 1. That's the 16-bit counter, and everything I'm going to show you here is how I get down to square waves of a couple of hertz. Right, everything's happening a couple times a second. So I'm starting out with my 16 megahertz system clock, and then I have a prescaler of 64. That is, I'm going to configure the timer for normal mode, prescaler of 64. What that means is that the clock frequency into the timer is going to be 16 megahertz divided by 64, which is 250 kilohertz. So we'll be driving this clock at 250 kilohertz. It's coming from our 16 megahertz system clock being divided by 64. So that means that each cycle of that clock, or of the timer, is 1 over 250 kilohertz, which is 4 microseconds. So every time it ticks, tick tock, tick tock, tick tock, it's 4 microseconds. So each count of the clock is 4 microseconds long. And so I'm going to show you code where I have a variable called pitch. And pitch is another way of saying frequency. What's the pitch of that? And I'm going to be varying this. And the result is going to be, I'll sort of skip through all of this, and I'll just tell you that I'm going to be generating a square wave that has a value here. It's pitch, which will just be a number that we're changing, divided by 1.9. Pitch divided by 1.9. And I feel like there might be a mistake in that. It might be pitch times 1.9. It's not important right now. What I'm going to do is I'm going to show you the code, and then I'm going to show you the demo. That's what matters. Okay, so here's the code. I call this ramp frequency. Where if you think about what a ramp is, a ramp that you walk up on, it's something that sort of linearly increases. So what I'm going to be ramping up the frequency in this code. So it ramps or it increases the frequency on pin PD6 every time a button is pressed. So that's the game. I'm going to be just playing this square wave, and we'll be playing it attached to the output to PD6. I'll have a blinking LED. I'll have a piezo speaker, and we'll see it on the scope. And then every time I press the button, it's going to approximately double the frequency. Okay, and just to walk you through the code a little bit here, here we're configuring the timer. Right, we're configuring it to normal mode and then divide by 64. And then in this code here, what I'm doing is I have this variable called pitch. I start out at 1. And what I want to do is I want to double that value every time I press the button. So if you look in this code, if the button is pressed, then just take pitch and multiply it by 2. So every time you press the button, you want to double this value. And then that value is impacting the value that we preload into the counter. Now, a thing about this loop is happening fast. And so one of the things about when you put your finger on the button, if I just had this code like this, right, and I kept my finger on the button, or even the time it takes to press a button, right, it takes you a certain number of milliseconds just to press a button. And unless I put a delay in there, which I put in down here, I have this statement. I'm checking to see if the button is pressed. If it is, I'm multiplying pitch by 2. Then I'm introducing a delay of 0.2 of a second. If I don't do that, what will happen is every time I press the button, it'll run through this loop many times. So I'm just doing this down to deliberately wait until I've had enough time for me as a human being to lift my finger off that button. I'm going to show you more about that kind of thing after we do assignment number 4. But anyway, the next code here is just counts up the timer and waits for the overflow. So let me show you the demo, and then we'll come back and look at the code. Okay, so I'm going to run this, and this is just me narrating it. So I'll go ahead and run it. Okay, so here's the setup. I've got the 328p configured to create a square wave using the 16-bit timer. That's timer number 1. I've already flashed code to it, so it's just running continuously with a square wave. And the output of that square wave on pin PB0 is going both to this LED here, and it's also going to a little piezo speaker. And then I'm also monitoring that with this analog device's scope, and that's what you can also see on the screen. And so you see the square wave on the screen, and it's reading a frequency of 1.9 hertz. Now I'll go ahead and connect the speaker, and you can hear that clicking. That's the piezoelectric speaker, and it's clicking at 1.9 hertz. Click, 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 click. And you can also see the LED blinking. I'm going to darken the lights in the room. We can have a better focus on the blinking LED here. Okay. Just notice here, you should be able to hear that clicking. I'll cover it up. Okay, you don't hear it clicking. All right, now what I'm going to do, let's zoom in a little bit. I've got a button here, and every time I press this button, it's going to double the frequency. So you'll see the LED flashing twice as fast. You'll hear the clicking twice as fast, and then on the scope, you'll also be able to see that it's telling you the frequency. Here up, you'll see the waveform, and here the frequency is 1.9 hertz. So let's go ahead. Click it. So that's 3.8 hertz. Notice it's clicking a lot faster, and it's blinking faster. Double it again. Oops, it looks like I hit the button twice that time. So now we're up to 15 hertz, and I can still see the LED blinking, and you can sort of barely see that there in the video, and you can hear the clicking. It's just clicking a lot faster. Okay. Now when I go and click it again, we're up to 30 hertz, and I can barely tell that it's clicking. Let me just change the time base there. So it almost looks like it's steady, you know, and that's the retinal persistence effect. And you can hear the buzzing. Okay, now let's go even higher, 60 hertz. And now you can no longer hear clicking, you're just hearing a continuous tone with your ear. And the LED looks like it's on all the time. So you have the effect of retinal persistence here, and then you also have the way your ear is perceiving that sound. It's really just turning into a tone now. You can't hear the clicking anymore. Higher. So that's 240 hertz. Okay, that's 470 hertz. Okay, 905. Now clearly you can't see any blinking of the LED. It just looks like it's on all the time. But we can hear that tone getting higher in frequency. Right, there's 1.6 kilohertz. Okay, 2.975 kilohertz. 4.8. 6.9. So we're not actually doubling. The algorithm's doing something a little different, but we're making the frequency higher and higher each time. So that's 6.9 kilohertz. 8.9. Now that pitch is so high, it's about at the top of my hearing, just about. So I can still hear a high-pitched squeal. Okay, that's 10.4 kilohertz. I don't hear that. Okay, now we've gone back to 0 again. Okay. That's the end of that. Okay, so I wanted to show that because I thought it was an interesting application of the timer counter that we're working with, and I also wanted to sort of give a sense of things that happen on human scales, you know, and how we can see an LED only at low frequencies. and then we hear things at higher frequencies, you know. But this is just an example of the kind of waveforms that you can create with the 328 or with a microcontroller. Just to take another examination of the code that we just created, it's the same code that I showed you in the previous slide, but I rearranged it to use functions. And you know, I'm a sort of a believer in using functions when I can. And what I did is I took all of the details, all the guts that are needed to configure the timer, and I packed those away in some functions. And so let's just take a look at main here. You know, you should always be able to, when you're looking at code, you should look at main and be able to look between the block comment up top, tells you what's going to do. Then you look at main, you should say, okay, I get it. I get what's happening in this. So let's look at that function, and let's look at that block comment. It's going to increase the frequency of a square wave on PB6 every time a button on PB0 is pressed. Okay. So I've got sort of the usual, you know, setting up of pins and things. Down here, I have a function called timer1init, and that's down here. And this will initialize the timer. And to do that, all we're doing is we're writing to TCC R1A and R1B. We're giving them the right numbers so that we can cause that timer to count up in normal mode and divide the clock by 64. And then in the while loop, I have this business that I talked about checking the switch. Then here, I created a function called delay, and I pass it the variable pitch. That's this variable that I'm creating. And down here, all of the details of the counter, waiting for the rollover flag and all that, are handled that way. So we initialize. I'm waiting for the button to get pressed. Every time I press it, I change this variable called pitch. I have a little bit of delay till my finger comes off the button. Then I actually execute the delay in a function, meaning the counter starts with the appropriate value, counts up to the top, overflows, all that's taken care of in the function. And then I just toggle the pin PD6. And that toggling was being done on both the LED and on the piezo speaker, and we were seeing that on the scope. Okay, and so just to, before I move off of this is normal mode. I just want to look one more time at that and review what we've just done here. And we did a similar thing in class on Wednesday of last week. So what have we just done? The first thing we did is we configured timer 1. And how did we do that? We wanted to configure it for normal mode and then divide the system clock by 64. And so I had these two lines here. And you can put those in main, or you can put them in a separate function, and I happen to call it timer init, right? I think that's a cleaner way to code. Then I had the core timer delay loop, where we preload a value into the timer, right? And then the timer is going to count from that preload value up to the top. And what is the top? If it's a 16-bit timer, the top is 65,535. Okay, so again, we preload a value into the timer, and the counter will then count from that preload value all the way up to the top. What's the top? Depends on how many bits in the timer. 16 bits, 65,535. We wait for the overflow to occur. We had to clear the overflow flag. Now I wanted to just point out, this business of needing to clear the overflow flag is what I call a quirky feature of AVR microcontrollers. The 328P is one of many microcontrollers. MCU just means microcontroller unit, but the 328P is one of many microcontrollers in the AVR family, now produced by Microchip. And it has some kind of quirky features, and one of them is that you have to clear this particular overflow flag sort of manually with software. Okay, and then after that, we just toggled the output pin, and this was the code to do all that. And then the result was we were taking our output on PD6, right? We played that into an LED and a speaker, looked at it on the scope, so we're interacting with the world with that, right? And then we got a waveform like this. And I also had my button on PB0. So this is a system, it's an embedded system that you can think of as a sense and response system. It's sensing and responding on human scales. I'm pressing a button. I had to put a delay in that code that looks for the button press, because when I take my finger and on my human time frame press it down on a button and come back, That's taken me 1/10 of a second or more to do that. And so you don't want it to keep on doing something every time that button is pressed, because it's going through this while loop very, very fast. So I deliberately put a slowdown delay in there. My finger's on the button, it'll change the variable, the pitch variable, then it waits enough time for me to get my finger off that button. Okay. And also when we were looking at the output, we wanted to make sure that we set up the frequency that we could see and that we could hear. So we were really in our configuration, what was important is to divide the clock by 64. That's so I could get this whole thing to be responding on a time scale that we as humans can work with. Okay. Changing gears now. All right, so goodbye normal mode counter. So that's all fun. We generate things that blink and all that. Now we'll talk about something different, right? Same timers and counters, but a completely different mode. And so now I want to talk about using these timers, these timer counters or timers, as waveform generators. Okay. Now what's going on is the timers have built into them some circuitry that you can tell it. Once you set it up, it will just run by itself and it'll create waveforms for you. And you can access those waveforms on certain pins on the microcontroller. So you have timer 0, right? And it has 2 waveform generators. So it has waveform generate. It will create a waveform that you can access on this pin. You can access it on, it's called output compare register 0A and output compare register 0B. Well, first of all, the 0 comes about because this is timer 0 and it has A and B. If you're looking at timer 1, it's OC1A and OC1B. All right, if it's timer 2, it's OC2A and OC2B. Why it's called OC will become a little bit more clear as we go along. But the point here that's important is that there are these dedicated waveform generators. You set them up and they'll start creating waveforms that you can use. And they are internally wired up to some specific GPIO pins. So take a look here. It says OC0A. That particular waveform that you set up, it also makes use of pin PD6. So if we go down to pin PD6 down here, you'll see that it has many things. It's PD6, it can function as PD6. It can also function as PCInt22, OC0A, and all these other things, right? These pins all can do many things. And it turns out that to access this particular waveform, once you set it up, you access it on that pin. Okay, and I'll show you how to do that. And likewise, each of these has a specific pin that you'd have to access in order to access that waveform. So what we're going to do is we'll configure the waveform, set it the way we want, set it up and running, and then it'll just happen. You'll just have this, it's like having a function generator there on your chip, providing you an output at this particular pin. And so it uses, there are 6 of these waveform generators, and they use 6 pins. Okay, now just for your information, okay, so we have, I've shown in red where all those pins are. Okay, for those of you who are familiar with using the Arduino Uno, you may be aware, like if you're writing scripts for Arduino Uno, you may notice that some of the pins can be used for pulse width modulation. Right? They actually have a little symbol like this, a tilde symbol. And in the Arduino Uno programming lore, they tell you that if you want to do pulse width modulation, you use these pins for that. You can do pulse width modulation on those pins and those pins only. Why? Those are the pins that we're talking about here. All of these pins are the pins that we're talking about here. So what we're sort of getting at, if you may be familiar with using pulse width modulation on an Arduino Uno, I'm showing you what's under the hood for that. The reason why an Arduino Uno is able to give you pulse width modulation on these particular pins is because those are the pins that are wired internally to these waveform generators. Okay? So now, this is going to get, we're going to kind of get down into the weeds here when I show you how this works. And what you want here is sort of the big picture of this. All the gritty details are not all that important for you, but you know, it may be that you're called upon at some point to actually implement one of these waveform generators, and I wanted you to have seen how it works. So what I want to do is I want to show you, take a look at pin PD6. This is all in the textbook, and you'll find this in the chapter on pulse width modulation and motor control. The use of timers is actually spread out across 3 different chapters of the textbook, so that does make it kind of tricky. And I made reference to those chapters on the Moodle page. Okay, how is it that one pin, PD6, how can that pin do double duty? How can it be PD6 or this thing OC0A, the output of a waveform generator? Well, we've been looking at GPIO, general purpose input and output, and you know that when we did that, we had a data direction register. So if you configure the data direction register, what that's doing is it's really setting up a driver amplifier. And if that amplifier is on, it's forcing this to be an output pin, and when that amplifier is off, it's an input pin. And then you could write values to that. Okay, so that's sort of a simplified view at how GPIO works at the pin level. How do we bring these waveform generators? Well, let's put all this additional circuitry on there. And this box, well, so we're gonna focus on these 2 pins down here. But before we do, this device up here, right, is a multiplexer. That's a multiplexer. And what that'll do is it's a digital multiplexer. It's going to select this this pin here as either this input or this input. Okay, so it will either pass through whatever we've got in the port register, or it'll pass through the output of the waveform generator. And it does that by controlling this input line, right? And if that input line is a 0, then it will take it'll actually function as a GPIO pin. Whereas if this input line is a 1, what it'll do is it'll take the results of this waveform generator and pass that to the output. So in this manner, this one pin through this multiplexer can choose between 2 different inputs and determine which one it's going to send out. So now let's look at this selector line on the multiplexer. Well, that's an OR gate there. So what it's got 2 lines, and there's an OR gate there. As long as one or the other or both are high, then that's going to cause this waveform generator to be sent out instead of the GPIO. And so it turns out that the bits COM-OA1 and COM-OA0, right? These bits here control. They're part of the TCCR0A register, and they actually will control whether that pin is going to function as PD6 or is going to pass on the output from this waveform generator. Okay. Now it's very easy to get lost in all of the acronyms and the letters. It's called O0 here because we're looking at timer 0. It's called A because each timer has 2 of these waveform generators, and we're looking at waveform generator A. And then there are 2 bits, so they're called 1 and 0. Okay, and so I'm going to actually give you the numbers that you have to put in there, but I wanted you to have a sense of how it works. So everything we've got here is replicated inside the chip for every one of these timers. So there are 6 timers. All of that stuff is happening associated with the waveform generator for each of those timers. Okay, so that's sort of what's going on behind the scenes there. And the way we're going to configure this is, and we're going to just choose one of them, but we're going to configure it, this waveform generator, to give us a variable duty cycle waveform. And we call that pulse width modulation. So the idea is that we're going to generate a waveform of a certain frequency, and then we will vary the width of the pulse. So here you'll see it's on for a small amount of time, and then it's off the rest of the time. It's actually on for 20% of the time. So it's on for like a quarter of the time, it's off for 3/4 of the time. You call that 25% duty cycle. Or you can turn it on for half the time, and then off for half the time, 50% duty cycle, and so on. Or you can leave it on all the time, 100% duty cycle. You call that pulse width modulation, because what we're doing is we're modulating or varying the width of that pulse. And so I'm going to show you how to configure one of these waveform generators to vary the width of that pulse. You keep the frequency of the waveform the same, right? That is, this period here isn't going to vary. We're going to set that up, with our external clock and our prescaler and the total span that it's counting. That'll set that frequency. But what we'll be doing is we'll be varying the width of that pulse. And it turns out if you take this waveform and you feed that into an LED, your eye will believe that the LED is dim in this case and very bright in this case. And that'll happen because your eye is going to see this thing on for a short period of time, and then it'll be off. And so your eye, because of retinal persistence, which we've talked about, will be fooled into thinking this is an LED that's only on about 20% of the time, or it's only on at 25% brightness. And then when you make this even larger, your eye sees it for longer, you're sort of remembering that for longer, and it will appear as being brighter to you. So that's the phenomenon by which your eye will perceive increasing brightness with this pulse width modulation. The motor is going to behave differently. You're going to feed the same waveform into the motor, but the motor is a device that can't respond really fast, right? It has its own inertia to it. So what's happening is, and you can think about this in a couple ways. When you have one of these on pulses, it turns the motor a little bit. And then when the waveform is off, the motor stops turning. It coasts a little bit. And if you turn it on for more and then off, the motor will actually coast a little bit more for each repetition interval. Another way of thinking about this is if you've had some instruction already where you've learned to think in terms of the frequency content of signals, and you know that a waveform that looks like this, it has a DC component, which is the average value, and then it has some harmonics associated with it. I'm talking about the Fourier series representation of the waveform. And the motor acts as a low-pass filter. It gets rid of all the high-frequency stuff, and it only responds to the DC or average value. And so what happens is that the average value of this one, the average value would be sort of the area under the curve divided by the period. The average value of that top one is smaller than the average value of this waveform and this one, right? And so what we're doing is we're changing the average value here with pulse width modulation. So let's go ahead and do this. So to configure it, I'm just going to give you the codes that you need to do it. It was these things that we had to configure. And so we're going to set those to 1 and 0. And if you go into the textbook and try to make sense of this, it's called clear the output comparator, clear that pin on compare match, set it at top. I'll show you what that means. You're going to clear it on compare match and set it at top. It takes a long time to make sense of that, and I don't expect you to have internalized that in this introductory course. These other pins, we're setting those for fast PWM mode, and we're using a 64 prescaler. So you just give it these magic numbers, and it's going to do this. Okay, a little bit about how this thing works. So the first thing we're going to do is we're going to configure the timer for fast PWM mode, right, using what I just showed you. Then we're going to load a particular value. We're going to load a number into this register, this output compare register. And the timer is going to be set to continuously count between the bottom and the top, between 0 and 255, or 0 and FF. So the timer is continuously counting between 0 and FF. But what's going to happen is that the output pin that we're going to be looking at is going to be set when the timer is on the top, and it's going to be cleared when the timer value reaches this value we loaded into a register. And I'll show you by example. So the green line represents what the counter is doing. The counter is always going to be counting from 0 up to 255, which is FF. And then it's going to go down to 0, and it's going to run up. So the counter is just free running like this. We're going to load a certain value into this register called OCR0A. When the timer is at the top, it's going to set this output pin, and it's going to remain high until on the next cycle the counter is counting up. When it reaches OC R0A, the output pin shuts off and it stays off. So what we're doing is we're setting this value high at the top of the counter, and then we're clearing it when the counter reaches this preload value. In this next example, I just use a higher preload value. So we set the timer and then we clear it when it reaches preload value, and we end up with a larger duty cycle. And so we can increase or decrease the duty cycle by increasing or decreasing a value that we load into OCR0A. Load that with 0, you'll get a 0% duty cycle. Load that with 255, and you'll get a 100% duty cycle. So code that implements that, here it is. It's very simple code now. So let's look at what this will do. It's going to create a 12.5% duty cycle waveform, and it's going to create it on this pin, because it's sort of wired up to give us an output of that on that pin. Okay. So we're going to use the timer 0 waveform generator A with a divided by 64 prescaler. And then just to go through the math, the waveform frequency here, the timer, it's fed with a 16 megahertz clock. It's divided by 64. And that timer is counting between 0 and 255. So it's going through all 256 states. That means it's a waveform of 976 hertz. So that's the basic timer waveform. And then we're going to load, I wanted an output waveform with a 12.5% duty cycle. 12.5% of 256 is 32. So I'm going to preload 32 into this compare register. So let's look at the code. The output is on P6. You got to use that for this timer. I initialize it with those registers that I gave you. All I have to do, now the timer is running. Now all I have to do is preload it with this value of 32, which is 12.5% of the way up. And when you do that, I'm going to go back to the previous slide. The timer in the background is going to be doing this, and we're going to see this waveform high, low, high, low, high, low. And it's only going to be on for 12.5% of the time. Okay, there's the circuit. All right. You won't be able to see 12.5% from an LED and make sense of it. So instead, I thought I would just show you what it looked like on the scope. It generated this waveform, and you can see it's only high for a small period of time, and then it's low the rest of the time. That was 12%. So it created a 490 hertz pulse train with a 12% duty cycle. Okay, now if I change the code, instead of a 12% duty cycle, maybe a 90% duty cycle. So this should actually be 90%, 90. Okay, and so to get 90%, what I want to do is I want to preload it with 90% of 256, which is just 230. So I just load it with that. Yeah, so I've got a question. Can you change the divide down to change the PWM frequency? Yes. Yes, you change the frequency by changing the divide down, and then you change the duty cycle by changing the value that you load into here. Okay, and so I'm going to run the same code, and you can see here it's on for 90% of the time, and it's off for a small period of time. So that's 90% duty cycle. Okay, so now I've got another code that is going to run through and ramp through all the different duty cycles. Okay, and so let me show you how I'm doing that. I'm initializing the counter, and then I've got a while loop. I've just got this variable I, and I just keep adding 10 to it. I start out with I at 0. So the first time I come through it, I is going to be 10. Then the next time it's going to be 20, and then 30, and 40, and 50. And I'm preloading, I'm loading that register with all of these values between, between 0 and 10, 20, 30, 40, so forth. And what that's going to do is it's going to set that register. It'll give me a waveform at an appropriate duty cycle. And then I'm waiting. I wanted to just sort of wait so that it'll play that duty cycle for a certain amount of time. And I'm making that 250 milliseconds. Okay. And so to see what that code is doing, this is me taking now my iPhone and taking a video of what you see on the screen and the LED. So you're going to try to focus on the LED and see if you can pay attention to the brightness of it. And as I run it, what you're going to see is the duty cycle here will be changing. The frequency is fixed. The duty cycle will be changing, and you'll be able to correlate that duty cycle with the brightness. And I may have to run it a couple times. You notice how it'll go from here, it's off, it's very dim, and then it gets brighter. Okay, off, dim, brighter. Okay, so what this code is doing is it's just gradually increasing the duty cycle, and you're seeing that being manifest as a changing brightness of the LED. And the LED's brightness isn't changing. It's just on for a certain percentage of time. But your eye and brain are perceiving that as being changing brightness. So that's what you want to do for the homework assignment. And you've got all the elements of the code that you need right here. I'm going to show you next what happens when I take this and hook it up to a motor instead of the LED. Okay, same code, but the wiring is a little more complicated. So if you want to drive a motor with a GPIO pin, then you can't do it directly. So it turns out that these GPIO pins here, they can only source up to 40 milliamps of current. You just can't get more than 40 milliamps of current from one of these things. And a motor, even a toy motor, when you turn it on and have it running with no load on it, it draws a couple hundred milliamps. So if you hooked up a motor directly to the GPIO pin, the motor wouldn't turn on. You put the pin high, the motor won't turn on. And if you put a voltmeter on the pin, you'd see that its voltage just dropped down to almost zero. That output voltage just collapses when you try to pull too much current. So what you do is you use a transistor interface circuit. And I've chosen a Darlington transistor here, and it serves as a motor driver. And what we're doing here is we're using the GPIO pin to turn on the transistor. And the way a transistor works is you turn it on by controlling both the voltage and the current going into the base. It's the current going into the base and the voltage between the base and the emitter. And it only takes a small amount of current to turn that transistor on. But when the transistor on, it acts like a switch, and it allows current to flow from the collector to the emitter. And if you take the motor, you connect one terminal of the motor to this collector, and the other one you connect to a power supply that actually can provide the current needed for the motor. So what happens is the transistor turns on, it's completing a circuit between a power supply, the motor, and then through to ground. All right, the transistor just completes that circuit, and the motor gets its current directly from the power supply rather than from the GPIO pin. That's the key here. The GPIO pin is providing the control, but it's not sourcing the current for the motor. That's coming directly from the power supply. Okay, so my plan was to have you go ahead and build this. I've been assigning this for 10 years in assignments. When I did it, I had nothing but problems. The things were resetting. Everything was just resetting on me. So I ended up getting some laboratory power supplies that I have, hooking up the motor to those, so that instead of the motor being powered by, the 5 volt, the same 5 volts that was powering my 328P, I use these benchtop supplies. So what I'm going to show you here, when I get this going, is you'll see the circuit. You'll see an oscilloscope display, which is going to show you the varying duty cycle waveform. You'll hear the motor, and I've got a voltmeter, and I'm measuring the DC voltage going to the motor, and you'll see that increasing as I do pulse width modulation. So let's go ahead and run this. I'm going to hook up the motor in a bit. Here, I'm going to hook it up. Can you hear that okay? Okay, so
Yeah.
okay, so so a couple things that are interesting about this. I mean, when the duty cycle was low, the motor is just starting to turn on and it makes one kind of noise. And as the duty cycle gets higher and higher, you're hearing the motor go faster. The other thing that's interesting is I'm looking at the DC voltage that's being applied to the motor, which is just the output of that pin, right? So, and right now it's reading 1.29 volts. But if I go back and show you the video again, focus on the reading on the multimeter. Focus on that. Well, let's see if I can pause this. Okay, what is the DC value of a waveform? I mean, if you look at this, do you see some DC in there? You know that a waveform has AC components and DC. DC, the direct current part of a waveform, is nothing other than the average value, and that's precisely what you're measuring by that voltmeter. So that voltmeter is able to measure the average value of that waveform. Okay, now if you want to get the average value, if it's a periodic waveform, you can look at it over one period, right? And you ask, what's the average value of that over a period? So that means it's going to be, it's this area here, right, divided by that total span. That's this corresponding average value, and that's what's causing the motor to respond. The motor is responding only to the DC value, and as that gets higher, the motor is going faster and faster. The motor is filtering out, or it's not responding to, the higher frequency structure in this, and that's because the motor has all this mechanical inertia in it. Okay. Anyway, this is a sort of a fun and interesting thing to do, and it's important to be able to use and think about motors. But you've got enough complexity in this lab, just getting your chip working on a board, getting it programmed, getting a battery, getting it flashed, getting all those pieces together. It's enough complexity there that I don't want you, in addition to that, to be dealing with a motor that's generating electrical noise. So if you did want to, I just want to show you this. I did try to do an experiment where I'm just looking at the, this is just using a power supply, a clean power supply here, and I'm increasing the voltage with my hand. I'm increasing the voltage. And look at what that voltage looks like. Look at these spikes that show up. It's 2 volts per division here. So occasionally you're seeing these spikes that are about 5 volts. This is what was causing everything to reset. So again, this was just me with my clean laboratory power supply, and I'm just with my hand, I'm dialing up a knob to change the voltage, and that's a clean DC voltage. But I'm looking at that voltage after it's hooked up to the motor, and I'm looking what the motor does to that voltage. And you can see sometimes it gets very, very noisy, and it has these spikes that are occurring that are several volts tall, which is wreaking havoc on everything else that's connected to that motor. Yeah. So I've got people asking me, is this due to the inductive loads? This is you've seen this in a circuits class. The motor has several things in it. It has these brushes that generate sparks, which generate electrical noise. The motor also has inductance because of the windings of the coil. And when the current decreases through a coil, it generates a voltage spike. You may remember you know, the voltage current relationship for an inductor, V is L di dt. So if you have a sharp change in current, you can have a large voltage spike. And so as we're changing the power going to the motor, it's creating these spikes. So that's what's happening. So if you actually wanted to do this with these motors that we've got, because they're so electrically dirty, this circuit wouldn't be sufficient. You'd have to, the first thing that you'd have to do would be you'd put a diode here. This is called a flyback diode, and that causes, it helps to suppress some of the noise. It has to do with this inductive transient. But more significantly, this is an opto-isolator. This is a device that actually has a photodiode and a phototransistor. And when you turn on this pin, it's causing some light to be sent from the photodiode to the phototransistor. So the right side and the left side of this circuit are optically coupled, but they're not electrically coupled. You completely separate the motor from all of your sensitive electronics, and the only connection is happening optically, so you do not have an electrical connection. You give the motor its own separate power supply, which is what I had to do here, and you build up a circuit like this. You don't have the parts, we don't have the parts in here, you know, to do that. So that's why I'm telling you, don't use the motors. Just make an LED glow. Okay, that's all, folks, for today. Any questions or comments on anything?
Yep. I would check the TA office hours. I think we have TA office hours posted after class, but you should double check.